Good morning, everyone. I am Meenakshi Tripathi, research scholar in Department of Mathematics in NIT Jamshedpur, India. Today, I will give my presentation on chaos synchronization, anti-synchronization, and parameter estimation in a chaotic system with coexisting hidden attractors. Now, I will start my presentation by introducing descriptor system. Descriptor systems, also known as generalized state space systems, singular systems, differential algebraic systems, are systems that are generally described by a combination of differential and algebraic equations. Such systems often arise in the modeling of many types of systems, including chemical process, biological systems, circuits, and many more. Also, one question arises in our mind that what is an observer? So, knowledge of the states of the system is important for feedback, but it is not always possible to measure all the state variables. So, in such cases, states can be estimated from the output of another dynamical system, which is called an observer for given system. So basically, an observer is a mathematical model which uses input and output information of a given inner system whose output asymptotically approaches to the true state value of the system. Another term that we have used in our work is an adaptive observer. So adaptive observer is similar to the observer. It is different from observer in the case of in the case where we need to estimate the unknown parameter as well along with the state vector. In our work, we have considered the system which is given by equation 1, where x is the state vector, theta is the unknown parameter, f is the nonlinear function, and y is the output of the system, which is a linear combination of a state vector and the unknown parameter theta, and A, B, C, D, H are known matrices of appropriate dimensions. Here, our objective is to estimate the state vector x along with the unknown parameter theta. For this purpose, we will rewrite equation 1 into the descriptor form, which is given here by equation 2 by defining the augmented state x is equals to x theta, where x is again a state vector, y is the output of the descriptor system, E, A, C, H are the known matrices, and where A, H, C have the form which is given by equation 3. Now, in our work, we have taken 3 cases for designing an observer. First case is the synchronization, second case is anti-synchronization, and third case is switching between synchronization and anti-synchronization. In case of now here first we have considered observer designing in case of synchronization. So for that purpose, we have made some assumptions. The first assumption is that rank of E transpose and C transpose should be n. This case is very important as this case will help us to construct the LMI later. The second condition is that F should satisfy the Lipschitz condition, which is given by equation 4. Here lambda F is the Lipschitz constant. Now we can give our observer after defining the assumption. So observer in case of synchronization is given by equation 5. In which our objective is to determine the matrices N, L, R, and M such that x cap becomes the estimation to the state vector x as t tends to infinity. Here is the algorithm for computing observer matrices N, L, R, and M. So for this, firstly, we compute the matrix R. After computing the matrix R, we will compute the matrix E tilde, A tilde, which is corresponding to the equation 6. And after computing E tilde and A tilde, we will check the solvability of the LMI for positive definite matrix P, A tilde, and scalars Z and beta, which is greater than 0. Now, if LMI 7 is solvable, the observer matrices can be easily computed from equations 8, 9, 10, and 11. Here is the second case, second case of observer design. This is the case of anti-synchronization. This is the special case of synchronization where the aim is to have the observer system synchronized with the opposite value of the states. That is, x norm of x plus x cap tends to 0 as t tends to infinity. So in this case, for designing an observer, we have again some assumptions on our system. So assumption one is valid for this case as well, and the assumption two is that f should be an even function and f should be satisfies Lipschitz property, which is given by equation 12. Now, the form of the observer in case of anti-synchronization is given by equation 13. Here, our objective is to determine the matrices NA, LA, R, and MA such that X cap becomes the approximation to the state vector X. Now, in our work, we have proposed a theorem for designing an observer matrices in case of anti-synchronization. The theorem says that the observer 13 anti-synchronizes with the system 2 if the LMI 7 is solvable for positive definite matrix P, A tilde, and Z beta greater than 0. Then we can easily compute the observer matrices K, K, NA, MA, and LA by computing the equation 14, 15, 16, and 17. So for the proof, firstly, we will consider the aerodynamics term EA is equals to x plus x cap. Now, putting the equation 16 and simplifying, we get the equation 18. Now differentiating this term and putting the equations 15 and 17, we will get equation 19. Now to stabilize the equation 19, we will consider the candidate Lyapunov function, which is given as V is equals to EA transpose PEA. After differentiating it and simplifying and putting the equation of value of equation 12, we get the equation 20. Now, if condition 7 holds for positive definite matrix P, A tilde, and Z beta greater than 0, then V dot will be less than minus beta EA transpose EA, and the aerodynamics will hence converge. Now, this is the last case of observer designing that we have considered in our paper, is the case of switching between synchronization and anti-synchronization. The two designs in this case are combined together into a switching observer that can perform both tasks of synchronization and anti-synchronization according to the value of switching signal. Now we are able to construct this kind of observer just because of similarity in the case of synchronization and anti-synchronization in LMI. Now, LMI in both of the cases are similar. Also, the matrices observer matrices are similar. For example, N is similar to NA. MA is similar. MA is the reverse of minus. MA is reverse of M, and LA is reverse of L. Also, the observer in both of the case, that is the case in case of synchronization and anti-synchronization, are same. So here we can consider the case of switching between synchronization and anti-synchronization. For that, we have proposed a corollary which says that if ST be a switching pulse signal varying between the values of 1 and -1, here 1 indicates synchronization and -1 indicates anti-synchronization. So under assumptions that we had taken in say case of synchronization and anti-synchronization, a switching observer can be designed by combining the designs of the synchronization and anti-synchronization as follows. First step is to compute the matrices R, E tilde, and A tilde, as we have computed in the case of synchronization and in the case of anti-synchronization. The second condition is to check the solvability of the LMI 7 for positive definite matrix P, K tilde, and Z beta greater than 0, and to compute the matrices K and ML from 8 to 11. And once we will compute the matrices N, M, L, and M and L, we can easily compute NA, MA, and LA of L. Now, during the simulation, the observer switches between 5 and 30 depending on the value of the switching signal ST to either achieve synchronization or achieve anti-synchronization. Here is the example that we have taken in our paper, the example of chaotic system, which is given by equation 21. Now, for estimating the state variables x1, x2, x3, x4, and unknown parameters b and d, we have formed the augmented state x is equals to x1, x2, x3, x4, b and d, and which resultant into the descriptor system. Now we will design an observer for this system. Since this f satisfies the Lipschitz property, so we will first calculate the Lipschitz constant for this function, and which is given by the Jacobian of f, which is given by calculating the Jacobian of f, which is given by equation 22. Now, here is the simulation of observer design for synchronization. For that, we have taken initial condition x naught is this much, a is equals to 4, b is equals to 1, c is equals to 1, k is equals to 12, d is equals to 4.5, which is Lipschitz constant 21.9. For the observer simulation, we have taken z is equals to 1 and beta is equal to 0, and the initial condition is taken as that 0 is equals to this much, and the output matrix is taken as c is equals to this much. Here is the simulation of observer design in case of synchronization. Here, red line denotes the estimated state and the blue line denotes the original states. This is the simulation in case of anti-synchronization. Same output matrix we have taken as in the previous case. We had taken b is 4.5, that is 1, and beta is equal to 0. Also, the initial condition is same like x naught, and z naught is different here. The simulation in case of anti-synchronization is given here. Red lines denote the estimated states and the blue lines denote the original states. Here is a simulation of observer design for switching between synchronization and anti-synchronization. Same here we have taken a switching signal st is equals to this much, and the output matrix is same as in the previous case, and z is equals to 1. Here red lines denote the estimated state and blue lines denote the original state. Now, conclusion is that here in our paper we have considered the problem of chaos synchronization and parameter estimation. After that, state and parameter estimation is done simultaneously by constructing descriptor system. After that, we designed an observer that estimates the augmented system's state, and then design is then adapted to achieve anti-synchronization, and the unified switching observer is proposed. In future, we will consider the effect of the output. We will consider the system with having the effect having output disturbances, and the case of switch system will also be considered. And apart from synchronization and anti-synchronization, we will also consider the case of phase synchronization. These are the references. Thank you.